Hello! In this video, we are going to prove the following theorem. Suppose a and b are integers. Then a is greater than b if and only if a is greater than or equal to b plus 1. Now, in this series, we are using a list of 10 axioms for the real number system. And I'll leave that list of axioms in the description below. Now, in this video, we are going to be using axioms 1, 2, 4, and 5. Axioms 1 and 2 are just the commutative and associative laws. Axiom 4 tells us about the real number 0, and it says for all real numbers x plus 0 is equal to x. Axiom 5 tells us that every real number has a negative, and for all real numbers x plus the negative of x is equal to 0. And using the concept of the negative of a real number, we define the operation of subtraction, so that given any two real numbers a and b, we define a minus b to be a plus the negative of b. Now, in our real number system, the real numbers are equipped with a subset, which we call the set of positive real numbers. And we denote it as r plus. And using the set of positive real numbers, we have defined the greater than relation, the less than relation, the greater than or equal to relation, and the less than or equal to relation. And an obvious result that we've proven is, given any real number x is an element of the positive real numbers if and only if x is greater than 0. And some other results regarding the ordering of the real numbers that we have proven are as follows. We have proven for all real numbers x plus 1 is greater than x. We've proven for all real numbers a, b, and c, if a is greater than or equal to b and b is greater than c, then a is greater than c. And also, a is greater than b if and only if a plus c is greater than b plus c. And also, a is greater than or equal to b if and only if a plus c is greater than or equal to b plus c. And next, in our real number system, we have defined the positive integers as a subset of the real numbers. And we have proven that 1 is the smallest positive integer. More precisely, we have proven for all positive integers n is greater than or equal to 1. We've also defined the integers as a subset of the real numbers. And we have proven that the intersection of the integers and the positive real numbers is equal to the set of positive integers. We've also proven that the integers is closed under subtraction. So given any two integers a and b, we have that a minus b is an integer. Okay, so now let's get into proving this theorem. Now we're trying to prove a statement containing if and only if. So let's first prove the converse. So we're first going to prove if a is greater than or equal to b plus 1, then a is greater than b. And to prove that, suppose a is greater than or equal to b plus 1. Now, by L1, we have b plus 1 is greater than b. And also, let's remind ourselves a is greater than or equal to b plus 1. So I'm going to write a is greater than or equal here. So what we see here is, by L2, this implies a is greater than b. And that is exactly what we wanted to show. So we've shown if a is greater than or equal to b plus 1, then a is greater than b. So this proves the converse. Now we're going to prove the forward. So we're going to prove if a is greater than b, then a is greater than or equal to b plus 1. And to prove that, suppose a is greater than b. Now first, we're going to take this inequality and add negative b on both sides. We're justified to do that by L3. And next, by definition of subtraction, a plus the negative b is equal to a minus b. And by axiom 5, b plus the negative of b is equal to 0. So really, this inequality is saying a minus b is greater than 0. And since a minus b is greater than 0, well, according to this result, that tells us a minus b is an element of the positive real numbers. And also, since we know a and b are integers, well, since the integers is closed under subtraction, it follows that a minus b is an integer. So we see that a minus b is an integer and a minus b is a positive real number. That tells us a minus b belongs to the intersection of these two sets. But the intersection of these two sets is equal to the set of positive integers. So this tells us that a minus b is a positive integer. But since 1 is the smallest positive integer, well, according to this result, this implies a minus b is greater than or equal to 1. And now all we gotta do is add b on both sides. And we're justified to do that by L4. But then we can show that this guy simplifies down to a, and this guy is just equal to b plus 1. And we could show that by applying axioms 1, 2, 4, and 5, and the definition of subtraction. So first, by definition of subtraction, a minus b is equal to a plus negative b. And then, by axiom 2, the associative law, we can move these parentheses around negative b plus b. And then by axiom 1, the commutative law, we can swap negative b and b. And then by axiom 5, b plus the negative b is equal to 0. And then by axiom 4, a plus 0 is equal to a. And by axiom 1, 1 plus b is equal to b plus 1. So, through these equalities, we have shown that the left-hand side of this inequality is equal to a, and the right-hand side of this inequality is equal to b plus 1. So this inequality is saying a is greater than or equal to b plus 1. And that is exactly what we wanted to show. So we have shown if a is greater than b, then a is greater than or equal to b plus 1. And so at this point, we have proven both the forward and converse of this statement. So we are done. This completes the proof. And so yeah, that's pretty much it for this video.